Hello, today we're going to talk about buffering capacity. So buffer capacity deals with the amount of a strong acid or strong base added into your buffer before significantly changing the pH of your buffer system. So consider that, let's say we have a weak acid HA and our conjugate base A-. If I add in a strong base to that solution, it would react with the acid portion. If I add in a strong acid, it will react with the base part of that. And it will work to neutralize H2O plus A-, and then H2O and HA. Okay, so no matter what, it's neutralizing it. But let's say you run out of HA. You don't have any more HA. And if you add in strong base, that strong base is going to wind up in excess, and suddenly the pH is going to go up very rapidly. And let's say, same idea, you have a certain amount of your buffer system, you're going to, if you keep adding in strong acid, eventually you're going to run out of that conjugate base and you won't be able to neutralize anymore, so your pH will go down really rapidly. And so that's called the buffering capacity, and it depends on the specific substances that you're using, but also the moles. So the moles of each. And that's really important. The more moles of your components in your buffer, the better the buffering capacity will be. Also, if you want the buffer to be really useful for both base and acid adding in, you want them to be equal concentrations. Right? So if you have the same amount of HA and A-, then it will be equally effective against a base or an acid being added in. If you want it to more so neutralize acid, then you're going to need more of the A-. If you want it to more so neutralize base, you're going to need more of the HA. So it really depends on what the buffer system needs to be able to do. And then that will kind of depend on your capacity. So questions about this might indicate, like, we'll say, like, which of the following is the best at buffering, and when you add in H2O+. And so you want to pick the one that has both things in the system to form that buffer, but has more of the A- present. And we'll look at some examples of this. So more moles and closer to equal will give it a balance between the two. A lot of times they'll also need the buffer to be working at a particular pH. So you could use Henderson-Hasselbalch, pH equals pKa plus the log of the base over the acid. So in this case, you would then, try to find a target pH and the pKa of that weak acid and figure out what ratio do you need of both to reach that target pH. It's a little bit harder to figure out just because then you have to work backwards with the log, but it is doable. You just don't see questions about that very frequently. Okay, so in this example, a buffer is created using 100 milliliters of 1 molar benzoic acid and 200 milliliters of 1 molar sodium benzoate. So remember, the sodium doesn't really matter, it's forming that conjugate base. K for benzoic acid is 6.4 times 10 to the negative 5. pH for this buffer, so you definitely need the pKa. Let's take the negative log of the Ka. So it gives you the pKa is 4.19. Also, we're adding these two things together. Okay, so this one is 100 milliliters of acid, 200 milliliters of base. We need to find the moles of both of those things, so that when we add them together and create 300 milliliters, we know how many moles are present. So you're going to do the 0.1 liters of the acid, 0.1 liters, times the 1 molar will give us 0.1 moles of our acid. And then 0.2 liters here for the milliliters times 1 molar will give us 0.2 moles of the conjugate base. I'm abbreviating here. So to find the pH of the buffer, do it down here, we'll use Henderson-Hasselbalch, pH equals pKa plus the log of the base over the acid. So pH is going to be equal to the pKa, the 4.19 that we found, our base is 0.2 moles, our acid was 0.1 mole. So you take the log of that ratio plus the pKa, and that gives us the pH is 4.49. It makes sense because it's larger than the pKa, and you have more of the base. Now it says, will the pH of the buffer change more when an acid or a base is added? Will the pH change more? Well, the pH will change more when a base is added, because there's less of the acid present in moles in the buffer solution. Because there's less acid, there's a lower buffering capacity for a base being added, so the pH will be able to change a lot quicker when you add in the base with the weak acid solution. If you add in an acid, it will have more of the conjugate base that it can react with and neutralize, so it will take longer to see a pH change when you add in an acid. Okay, so we have 3 buffers here. It's using the same weak acid with a pH of 3.2 and the same conjugate base, but different amounts of each. It's asking us what is the pH of each buffer solution. So you're going to need to use Henderson-Hasselbalch equation. Notice you're adding in these moles and it's together in the 1 liter of solution. We can ignore the volume because we know that that's the total volume of the whole solution. So we don't need to calculate anything else with that. We can just go ahead straight to Henderson-Hasselbalch. pH equals pKa plus the log of the base over the acid. So 3.2 plus the log of the base over the acid. So we know the pH here is 2.90. For the second one, pH equals the 3.20 plus the log of the base, which is 1, over the acid, which is 0.5, and the pH is 3.50. And our last one for Z, 3.20 plus the log of our base over our acid. Now notice that this ratio is 2, just like this ratio is 2. So because that ratio is the same, the change in the pH will be the same, 3.50. So that is an interesting correlation there. So those are the pHs for each buffer solution, but it says which buffer will be the best at resisting a change to the pH when an acid is added. Okay. So we're adding an acid. We want there to be more of the base present. So buffer X is not the best choice there because that one has more acid present. So we're down between Y and Z. Now they have the same ratio of acid to base, but buffer Z is going to be the better choice because it has more total moles of the conjugate base present, so it will be better at resisting a change to the pH. So more moles, more capacity.